Myself. Okay. Welcome to the class. Let me pull up today's syllabus. All right. All right. That's not working. There we go. Okay. So here's our class page. Here's our schedule. Today is the 2nd of September, and we're going to talk about chapter 2 today after we finish catching up with the stuff that we're a little behind on because the first lecture didn't get fully recorded. All right. So that's where we are. And there's a reminder on this uh, section here. I'm going to have a guest speaker. And it looks like I have an error in this. May have to update that syllabus. Okay. All right. So let's go back and take a look at chapter 1. I added some things to the end of chapter 1, which I thought might help you all. So we talked about Amdahl's law, and I added a graph. So what you can see here, right, with Amdahl's law is that if I've got something that's 50% parallel, right, it starts up, and it becomes slightly more parallel, but it never can get more than a factor of 2 speed up. And likewise, with 60%, it can never go above this orange line. And with purple, it can never go above this line. So no matter how many CPUs I throw at the thing, if my percentage of parallelism is not high enough, then I can't make use of them. And if I've got 0.99% or 99% parallel, then I can get to this brown line and I can make use of 30 processors, but eventually it's going to also fail. And I just thought it might be nice for you to have a graph of that. And I made a graph of Gustafson's law, which looks a lot better. So you see what happens with the 50% so-called 50% parallel of Gustafson's law, which means it's 50% parallel on one processor. But because it scales up the amount of work with the number of processors, it looks like a straight line. And it just goes up steeper with a higher parallelism percentage. But in reality, if you want to think about it, by the time this one is getting up to here, it's 99+% parallel because it's scaling up the amount of actual work that's being done. Any questions about that? Make sense? Yes. Tristan? Okay. Yeah. So if I go back and I look at Gustafson's law, right? What we say is our total work is going to be W plus K times N, right? So K is sort of the amount of parallel work I have on one processor, right? It's the amount of work that could be parallelized on one processor, but the amount of parallel work, I'm going to multiply that by the number of processors. So I'm going to scale up the amount of parallel work with to match the number of processors I have with Gustafson's law. So this is the idea that I'm solving a problem, and if you give me more processors, I'm going to solve a bigger problem. And so I'm going to make my speed up. I'm going to talk about my speed up on the bigger problem relative to what I would have gotten on a single core. Right. So it kind of puts things in a different context because what happens, of course, is scientists who have scientific codes that they're running on bigger machines, you get them a bigger machine, they run a bigger problem. And so they get a benefit from the bigger machine, even though if you're just looking at Amdahl's law, you might not guess that they would, right? Because you're not counting on them to run a bigger problem. You're thinking of them running the same size problem. And if you run the same size problem with Amdahl's law, you get killed. But if you can run a bigger problem and the bigger problem scales better, then it all works out. Make sense? All right. And so when I talk about P here, I'm talking about this K over W plus K, where K is the amount of work I would use if I were on one processor. All right. So that's why that one looks so much better. All right. So that's what I added to chapter 1 for you. Because I was looking at it, I was thinking, a graph would really probably help. All right, let's go back to chapter 8, which we were partway through. And let me remind myself where I was. We were talking about readers and writers, I think. Um, so we had yes, okay, this is the one that we were looking at. So we were looking at an implementation of the readers and writers. And the way we did it is we wanted to say once somebody asks for a write lock, we don't want to let any more readers in because the problem we were concerned with our first write lock, readers and writers lock, was that if I had a bunch of readers and there was always a reader, then I could never get a writer in to do anything, right? So what I wanted to do is we can have more than one thread that owns a read lock on a piece of data. But when somebody wants a write lock on that data, wants the ability to modify it, then I have to wait for all the read locks to finish. Then I can do my write, and then I can allow the read locks to accumulate again. So this is how the setup to the class looks again. So I have my read lock and my write lock, and I just instantiate everything here. And I have the read lock method and the write lock method that just returns the relevant read lock and write lock. And now what the way this looks is when I want to get the read lock, I take my one inner lock, I lock that, and I say while writer is true, then I just await. And once the writer flag is clear, then I increment my read acquires. And then in my unlock method, I increment read releases. And if read acquires equals read releases, then I do a signal all, right? And do an unlock. And let me go back and fix that indentation. There. All right. Okay, so then I do my read releases, and if my read requires equals my read releases, then I signal all. And on my write lock, so what I do is I get the lock, I wait while there's another writer, then I set the writer flag to true, and then while read acquires does not equal read releases, I await. So I have to await twice in the write lock implementation. And then once I've gotten through this, right, then I own the write lock and no one else owns a read lock. And I can unlock this by just setting this to false, right? So the read lock unsets by doing read releases increment, and this does writer to false. Any question about that? Does that make sense to everyone? You have a question? What is it?
Said,
What's your name again? Kendrick. Okay.
I'm confused about the part where you said that. I think you said no one else could acquire the read lock.
Yes.
Why would that be?
Okay, so if you look at the read lock class, what it does, right, is it has this while loop on writers. So if it comes when I try to do a read lock, I first check to see that the writer flag is not set. If it is set, I sit there and I wait. So that means that once somebody sets that writer flag to true, right, then no one else can acquire a read lock. All right. Okay. All right. All right. So we did this reentrant lock. Okay, so a lock is reentrant if the same thread can acquire it multiple times. And this is useful when you have a thread that locks a lock and then calls for a nested method that locks it again. Okay. The locks package provides reentrant locks, but we'll show how to create one. So reentrant lock could look like this. So we have a writer thread is calling for a write lock for the second time, will deadlock on itself. And another example would be using a fair writer's readers lock. Okay, so what we want to do is thread one acquires a lock. Thread two tries to acquire the right lock and is blocked. Thread one tries to acquire the read lock again and is blocked because of the thread two, and that's a deadlock. So these are kind of motivating examples for reentrant locks. And the reentrant read-write lock class provided in the Java util concurrent package does not allow lock upgrades, i.e. holding a lock in read mode and trying to access it in write mode. Why? Anybody have a thought? If I'm holding a read lock and I just want to say, hey, upgrade me to write lock. Why doesn't it allow that? Yes. Hold on. Reagan? Reagan. The read lock would never get released. The one that I already have would never get released. And even if I somehow detected that, right? It detected mine. Think about this. I've got two different threads that have read locks, and they both decide, hey, they want to upgrade to write lock. Now, each of them, even if it accounts for itself, can't account for the other one, right? And so we have deadlock. So allowing it to upgrade could result in deadlock, and so it's not provided.
Do it at the same time on deadlock again.
So you have two threads, each have a read lock, and each wants to upgrade its read lock to a write lock. Each is going to wait for the other one to release its read lock. And neither one of them are going to, because they want to upgrade. They don't want to release and reacquire, right? So you can release and the lock and then acquire a write lock, but you can't upgrade it. You can't convert it from a read lock to a write lock is the point. Because if you tried to do that, if two threads tried to do that at the same time, they would deadlock. And you're just asking for trouble that way. I need to open my drink. Any other questions? All right. So our reentrant lock is going to identify the thread ID of the thread who locks the lock. And we're going to change, and it's going to only change something when no other thread is holding the lock and a new thread acquires it. So it's going to count the number of times the owner of the lock locked this lock. Incremented when the same thread calls, incremented when the same thread calls lock, decremented when the same thread calls unlock. And when the counter is 0 or the waiting threads are awakened. So here's how it could look. We have a lock, we have a condition, we have an owner, and a hold count. And we're going to initialize all those things. In our lock method, we're going to get our thread ID. We're going to lock the lock. We're going to check if the owner is me. If the owner is me, I'm going to increment the hold count and return. If the hold count is not equal to 0, and then I return right away after doing that. If the hold count is not equal to 0, that means that somebody other than me is holding the lock. And so I'm just going to await that. And at the end of this, when I get past this part, I'm going to set the owner to me and the hold count to 1. Okay, so if I get through the lock and for the first time, then the owner should be me and the hold count should be 1. If I go in the second time, right, we should just increment the hold count and return. And now that I'm looking at this code, this happens so often when I get in front of a classroom. I'm looking at this code, I see a bug. This won't work as written. Who sees it? It's actually quite obvious, so you'll be upset with yourself if I have to tell you. Yes. Hold count should be set to 1. I have one. I'm holding one instance of this thing.
Does that have something to do with setting the me back to the thread idea at the beginning?
No, that's not it. It's more obvious than these things.
Be that. Home count, wow. Labor term.
So in this case, right, this is correct, right? Because what happens is if the owner is me, then I increment the hold count and just return right away. And then if I get past this, that means the owner wasn't me. So I better wait until that hold count gets to 0. Reagan. The lock is never released. The lock is never released. Let's fix that. I can't believe I never saw that before. So the way to do this, right, the correct way to do this is with a try. And I'm sorry, I heard somebody say something. Was it a question?
No, I was agreeing with.
Oh, all right. Uh, all right. That looks better. Now, I was thinking about this because, oh, now the font is wrong. Where's the font size? Minus. All right. Slideshow. No, still too big. Minus. I think that'll work. There we go. Okay, so now you can see, oh, the indentation's wrong. Okay, so now you can see how it's supposed to work, right? I get the lock, and with the try finally, the unlock gets applied whenever I leave. So it'll implicitly happen before the return and at the end of the loop, at the end of the body of the method. Any questions about that? All right. The unlock method, where we remembered to unlock the lock, is going to say if the hold count is 0 or the owner is not me, throw new illegal monitor state exception. So this shouldn't happen, right? I shouldn't be able to unlock a lock that I don't own. And so that's what this is detecting. If I do own the lock and the counter is more than 0, then I can decrement it. I can check if the hold count is 0, and then I can signal. Any questions or thoughts? Yes.
How would you try to unlock a lock you don't have?
Oh, it's easy. I just say, lock.unlock. No, it's a common enough error trying to unlock something you don't have or free memory you didn't allocate or something like that. What's your name again?
Ryan.
Ryan. Okay. Okay. Right. All right. So it's a common enough thing to do. All right. Any questions on any of that? You're allowed to ask. Oh, you know what? I should be writing down people who ask questions. I forgot to do that because I am going to give you all credit for participation. So please make sure that you ask your question. Yeah, this is the implementation. Yes, we're using a regular mutex lock to implement this thing. And this is showing you how you can make it reentrant. All right. All right. All right, so semaphore. So far, we've seen mutual exclusion locks where only one thread can access a critical section at the same time. A semaphore is a lock with a capacity, an upper bound on the number of threads that can hold it simultaneously. It uses a counter to count the number of threads currently holding the lock. It's incremented when a thread acquires the lock and decremented when the thread releases the lock. So it has the acquire method and the release method. All right. So this is kind of a weird thing that very specialized use, but you want to have, a resource that only two things can get to at once, or three things, or some finite number of things. So I'm going to initialize with a capacity C, and I'm going to set my state to 0. And then I'm going to get a reentrant lock for lock and a condition. I'm going to get a new condition from the lock. When I go to acquire a lock, I'm going to lock the lock. And while the state is the capacity, that is, while the maximum number of the state is the count of the number of threads holding the lock, while that number of threads holding the lock is at the capacity, I'm going to just wait. Okay. And as soon as I get past this while loop, I'm going to increment that state variable. And then I'll unlock. In my release, I'm going to get the lock, decrement the state, signal all, and unlock. Make sense? It's pretty straightforward, I think. I mean, once you get the hang of these things, they're all pretty straightforward. All right. Now I added some things here. So here is one of the basic problems of programming with locks is that they are not composable. And that means you can't just look at one part of the code and understand how the deadlock happened, right? You usually have to look at the bodies of several methods and figure things out. And that non-composability is a big problem for locks, and it's one of the reasons why parallel programming with locks is so hard. I mean, it looks so simple, right? You say lock, do the thing, unlock, right? But you can get yourself into an infinity of trouble with this. So in this case, I'm going to have two variables, A and B, and I'm going to get a lock for each of them, lock A and lock B. And then I've got incr B, which is going to lock the lock. It's going to increment the integer B by some amount, and then it's going to print out the state of this non-compose object. And then it's going to unlock. And incr A is going to do the opposite thing. I mean, it's going to do the same thing except for the A variable, right? And these both look harmless enough. And then there is a print method, which is going to print out the state of the non-compose object. And it has to get both locks for that because it needs that to ensure that you're seeing a consistent view of the non-compose object. So, do you see the problem? Do you see why this class is doomed to failure? Because it is doomed to failure. Yes. What's your name again? Mackay. Uh-huh. Right. We're allowed to re-enter a lock. That's okay. What's your name? Matthew. Yeah, the incrementing it will increment to 2, and that's okay. We're allowed to re-enter the lock. We're allowed to have 2 instances of the same lock because it is a re-entrant lock.
So you only A is the issue that your lock B and B is is already locked by another.
You're heading in the right direction. Yes.
Might it have something to do with the order that you lock and unlock A and B?
Yes, it has something to do with the order. Well, it's the order of locking that matters. So imagine that I have threads 0 and 1. And thread 0 acquires lock A. Thread 1 acquires lock B. Now each of them tries to get the other lock. They're going to wait forever because they're waiting for the one the other one has, right? You see that? Yes.
Does finally execute after a return statement?
Yes. And you're Barrend. Okay. Yes, finally does. That's the whole point of finally. Right. Okay. So the problem is in Inker B, I first acquire B, then I acquire A, then I get a reentrant copy of B again, which is fine. The problem is with A, first I get A, then I reenter A, then I get B. So Inker B gets B first, then A, and Inker A gets A first, then B. And if they both run at the same time, then one will get A, one will get B, and then they'll wait for the other lock. And neither of them can get it because they're both waiting for the other one. Right? That's the problem. This is the fundamental problem with locks, is because it's so easy to do stuff like this. Okay, so actually I want to move these slides around. Now that I see them, I want to change the order. So hold on. Bear with me. All right. So this is the same thing, but a little more explicit, right? I get lock A first, I get lock B first, and I get a deadlock. So the order matters. So what I can do, right, is I can make this method called lock2. And what lock2 is going to do, if I pass it 2 locks, it's going to get a number for that lock. Now, Java has this thing called the system identity hash code, which is actually the value of the memory. That's the memory address where the lock object is being stored. And so what I want to say is, if A has the lower identity hash code, then lock A first. If B has the lower identity hash code, then lock B first, right? And now what I'm going to do with these two methods here is I'm going to ask for both of the locks at the same time. But whatever order I put them in here, this lock2 method is going to figure out which one I should call first. And so long as I always call them in the correct order, I won't deadlock, right? So that's an important thing that it took people a while to realize. I mean, it's kind of funny. Many times I've taught this course and I didn't state this explicitly because it just seems so obvious. But it's really only obvious after you've had a lot of hindsight. Simple a thing as this is, it requires, it's not intuitively obvious to people. So in this case, the ordering matters. So I avoided deadlock by just ensuring that I lock in the same order. So here are your keys to lock safety, right? Try to acquire mutexes in some canonical order. You need some way to decide which mutex should go first. You should try to keep code in the critical section as short and simple as possible. But you saw how easy it is to bring something else in, right? You do a print statement and poof, you've wrecked yourself. So try to keep it as short and simple as possible. Imagine you're debugging a class like that, right? You're debugging a class like non-compose, and something isn't behaving right, and you add that print statement to one of your methods, and suddenly your application deadlocks, right? Just because you added a print statement. I mean, so anyway, keep it as small and simple as possible. There's no guarantees in life, but that's what you're trying to do, is avoid any kind of method calls. Use try and finally, right? It's easy to forget to unlock something if you have multiple return points. Or if you have exceptions getting thrown or something like that. So try finally is your safest way to make sure that you've closed that lock. that you've unlocked that lock. And then even if we try to adhere to these rules as best as we possibly can, we're still going to have the basic problem that locks are not composable. We need to look at our entire code to really know what's going to happen. All right? So those are your takeaways for locks. And this should actually help you with your homework too, that I assigned, if you haven't done it already. Any questions? Okay. That takes care of chapter 8. Some more summary. Monitors allow, monitors, you remember that word? Monitors allow control of locks and conditions from within a single shared object. Conditions associated with locks allow threads to wait and release the lock until some property holds. Writers' locks manage access to a shared object when both are reading and modifying threads. Various implementations exist. There's a reentrant lock. There was a semaphore for multiple accesses to the critical section. Okay, so with that, we're done with chapter 8. Does it all make sense to you? You've mastered it all? All right. Well, if you ask a question, then I can address it. If not, I'm going to give you more stuff. So if there any part of that chapter was something that's still not making sense to you, now is a good time to bring that up. Ryan.
I feel we go right to chapter 8, chapter 1. I mean, I guess it's just the order of.
This is the order that makes sense to me, because I feel that most of you, if you've had any exposure to parallel programming, the fundamental tool that everybody faces first is the lock. And so I want to cover that first. The book wanted to build up to that, and I understand both methods of ordering, but I feel like by giving you chapter 8 first, I'm giving you tools to play around at a reasonable level as the course is going on, and while you're trying to figure out your own parallel programs and so on, it gives you the tools you need for that. Tristan.
So imagine you have a deadlock situation.
Right.
Like, way that you go about trying to figure out.
There are a number of things you can do, right? Like your IDEs might have debuggers that will help you walk through. There's also a special signal. I think it's 2 or 3, either kill 2 or kill 3, that you can send to a running Java process, and it will dump the stack trace of all threads. And sometimes you can say, oh yes, my code is stuck here and here, and that can help you figure it out. I've used that. But there are tools of that nature, right? And there are also parallel debuggers that allow you to just sort of step through things. There isn't the problem with parallel programming, right? Is there is not a procedural way that you can find the answer, because the problem may be that you don't even know how to reproduce the answer, as we stated before. And even if you do manage to reproduce it, it's hard to know what order of logic got you there. So it's really the worst debugging situation you can have is a parallel program. Any other questions? Hold on. McKay.
So.
Yeah, that I just invented. Yeah.
Yeah. So what actually can.
I mean, you have to come up with an order yourself. You have to just a way to order them. Just so long as it's always consistent, it's fine. I believe that C++, the lock guard constructor thing, well, if you give it several locks, it will do this kind of thing automatically for you. It will sort them. Because it's a standard thing people want to do.
So the order that you should acquire locks is always constant. Like it doesn't.
Right. You can come up with any ordering you want, so long as you're always consistent about it, you'll be fine. Because the problem with deadlock is always I have two threads holding a lock, and then they try to acquire the other one, right? And there's many ways to come to that situation, and the easiest way to avoid it is to just never do that, right? You never lock things out of order. All right. Any other questions? All right, let's go on to chapter 2 and see how far we get with that. All right. So in chapter 2, we'll take a step back in time a little bit with respect to chapter 8, in that what we're going to be doing with the other chapters is we're going to work up to seeing how locks work, right? We're eventually going to understand how to make them. And here, what we're going to do is we're going to start making them just out of memory, right? You've just got a computer with memory. How do you make a lock? And we're gonna go through this. Why is concurrent programming so hard? Well, I think you have a good feeling for it. I mean, it's you know, the metaphor here is you're trying to prepare a 7-course banquet by yourself with one friend or with 27 friends. I mean, it's enough work that it's going to be too much for one, but organizing 27 people is not necessarily easy. And so before we can talk about programs, we need some way of a language for them and how to describe time and concurrency. And so what we're going to do is we're going to come up with these pictures, and we have an event. An event is instantaneous. It takes like 0 time. It's just one point in time, one infinitesimal point in time. And there can be no simultaneous events, right? Because they're all exactly sometime. And then a thread, well, we have a notion of what a thread is, right? It's a thread is going to have a sequence of events occurring on it, and it's going to model what one CPU is doing. And we're going to put them in order. So A0 is going to come before A1, right? And that arrow thingy is going to be order. And, examples of events could be assigned to a shared variable or assigned to a local variable or invoke a method or return from a method. And there's lots of other things we could potentially put there. And threads are state machines. So everything that happens is going to change some state on the events are always transitions from one state to another. So, and there's a couple of special pieces of thread state. There's the program counter, right? And the program counter is a special like integer that's keeping track of what instruction you're executing. The machine has that internally. You never see it, but it's there. There are local variables, object fields, and so on. Okay, so we have concurrency. So we have these, on thread A, we've got these 4 different events, right? And on this thread B, we've got these other 4 threads, and this Tim should be time, and they're interleaving each other. So first these 3 happen, and then these 2, and then this one, and then this one, and that one. And what we want to try to do when we talk about our programs from here on is we're going to try to reason about the ordering or possible ordering of events on these 2 threads. So the point is these are going to be interleaved, and their behavior is not necessarily going to be independent, right? Because they might be mutating shared state. We also have a notion of an interval, right? Which we like to draw with it, which we like to use a capital letter, and it includes 2. It's the space between 2 events. So I've got events A0 and A1, and I got capital A0 in between them, which is that whole interval. And so, it might be this is when a method call starts, and this is when a method call ends, and this whole region in here is the time it takes to do the method call. And intervals can overlap, or they can be disjoint. And if they're disjoint, we can say that A precedes B, and we use that arrow notation, and we say if the end of event A0 is before the start of event B0, then it happens before or precedes. And it's never true that A precedes itself. And if A precedes B, then it is not true that B precedes A, right? And if A precedes B and B precedes C, then A precedes C. and A precedes B and B precedes A might both be false, right? If they were overlapping. So we say it's irreflexive, that A does not precede A. It's antisymmetric. If A precedes B, then B does not precede A, and transitive, right? That's a partial order. That's what we call a partial order. And then we have a total order, which is the same, except that it's required that either A precedes B or B precedes A. So we're going to have our events are going to be a total order, and our intervals are going to be a partial order. Okay. And then we can have an event can happen multiple times, right? We have like a while loop in this A0 and A1, and the first time it happens, it's A00 and then A01 and so on. Mumble is in these slides. Mumble is a stand-in for and so on or ... or etc. or whatever you want to think about it. It's just the author's favorite word. And so we're going to use that kth occurrence. We're going to use a superscript k to denote the kth occurrence of things. Any questions? No. All right. Okay, and so when we were talking about a counter before, and we look at the way a plus plus works, it's actually kind of like this. It's kind of, we have some temporary value that gets held, and we're going to upgrade it by 1 like this. And we want to make these steps indivisible using locks. And as we saw, a lock interface is going to look something like this. It's going to have lock and unlock. The actual Java lang concurrent lock interface has more methods on it than this, but we're going to stick with these for this discussion. So acquire, release. And so now this is the code that much simpler than most of chapter 8, right? We get a lock, we do a try, we do the temp, and then we do the +1, and then the unlock and return temp, and it's fine. The counter works. Acquire. I always forget that slides do this. Okay. So let the critical section, CS, the ith critical section, thread i's critical section, the kth time be thread be this, and then we have this for thread j, the nth execution is this, and then we have, and with critical sections, there's always going to be a total ordering. Either the CS of I is going to precede the CS of j or vice versa. And the reason that there's going to have a total ordering, right, is because of the very nature of the way locks work, right? They're mutual exclusion. And we say that something is deadlock free if some thread calls lock and never acquires the lock, then other threads must complete lock and unlock calls infinitely often. So that means I tried to lock, I failed to lock, but the reason I failed to lock is because somebody else keeps locking and unlocking before I get a chance. But the system as a whole is making progress because whoever that is that's locking and unlocking is making progress for my calculation. Okay, that's called deadlock free. I never got to execute, some thread never got to execute because of all the other things that were happening, but the system did not deadlock, right? It kept running. Okay, so that's a term for you, is deadlock free, and that's what that describes. Everything is running. It's not necessarily running fairly, but it's running. And then we have starvation free. And starvation free says that if some thread calls lock, it will eventually acquire the lock. And that means not only the system as a whole, but individual threads make progress. So starvation free is generally better than deadlock free, right? All right. Now we're going to think about ways to make locks, and we're going to have 2 thread solutions first to illustrate the basic ideas. And they, they fit on one slide easier. And then we're going to have n thread solutions. Okay, and we have this thread ID class that Java does not provide, but the book keeps talking about. So I have an implementation, sort of a reference implementation for you. And I just thought I'd throw it in here. So what we're going to do is we're going to get an atomic integer, which is a special kind of integer that means that if I have 2 threads that call get and increment on that object, they're each going to get different ints, right? that get an increment is going to happen as one atomic thing. And the way I'm going to, and then we have what's called a thread local variable. And a thread local variable is going to hold an integer. And I'm going to initialize it with this atomic variable. So each time a thread starts up, it's going to do this get an increment thing. And then if I want to get the actual value of the thread ID, then I say public static int get, and I return the ID store.get, right? So this initializes a thread local variable, which is static. That means it's global, but it's not global from the point of which thread I am. So each thread gets a number, and it starts at 0 and it goes up and so on. It all works. Make sense? Does it not make sense? Hold on, Berend.
Yes.
Okay.
What's the big behavior again? Then,
So the idea is every thread gets its own unique ID, and it starts at 0 and goes upward. Java does not provide such a facility. Okay. Okay, and so what we're going to do, and we have a convention, frequently in these slides, we're going to use I for the current thread and J for the other thread, right? If we have two, right? So in the case of threads that are, if I have two threads and they're 0 and 1, then I will be one of the threads and J will be the other one, because 1 minus I is going to be the other one. Make sense? All right. Okay. So here's our first guess at how to implement the lock. And so what we're going to do is we're going to raise a flag, because I set flag I to true. And then while the other flag is up, we're going to wait. So this is back to sort of chapter 1 thing, right? Where we've raised a flag, we look to see if the other flag is up, and we wait for it to come down. Now, will it be possible in this way for the lock method to succeed for two threads at once? So will I have, can I call lock with one thread and get through, and then call lock with the other thread and get through? Can that happen?
Well, I mean, you have to do it at the same time. They both call lock at the same.
If they both call lock at the same time, will they both get through it, or will one of them be stopped? Or well, okay, they could both be stopped, right? That's the problem with this, is they could deadlock. But the question is, assuming that they get called in order, right? First one calls, then the other one calls, then it's going to work, right? If they get called in order. Right. The point is, if they both execute this first line and then they both go on to the while loop at the same time, then it's game over. All right. Okay, so lock 1 satisfies mutual exclusion. So if we want to think about it this way, it has the safety property of not allowing two threads to get the lock, but it can deadlock. It lacks that safety property. So we have CSAJ can overlap with CSBJ, where that's critical section, or BK. And then we consider each thread's last jth or kth read and write in the lock method before entering. And we can see that it's going to satisfy mutual exclusion. If I raise my flag and I look for the other one and I don't see it, then I have the lock. So lock 1 fails deadlock freedom because a concurrent execution can deadlock, as you correctly identified. But sequential executions are okay. So here's another attempt. We have a victim, and we set the victim equal to I, and we didn't bother to initialize I with the thread ID.get, but we should have. And then I say, while victim equal I wait. So if we have two threads, and they each execute at the same time, and they both try and set victim, one of them will set it to 0, the other one will set it to 1, and then the other one will succeed, right? Any problems with this lock?
They can both set it at the same time. In one of the other examples we previously talked about, they had a solution where only one thread can set the victim at a time.
Well, okay, so rewind and repeat that for me, please.
Since they can both set the victim.
Right.
It may cause problems.
Well, what's going to happen is they're both going to set it. It could happen in either order, right? But once you set it, then it goes to look at it. And if it's still what it's the same thing it set it as, it's going to stop. But if the other one, if it interleaved, right? If I set victim equal to 0, and then right after I did that, the other thread set victim equal to 1, then I'm going to get the lock, right? So it's not going to deadlock. If that's what you're thinking. I'm not sure if it is. It's not going to deadlock. Matthew.
Other red set I while you're doing that while you're right there.
But what could I do that would behave badly?
You can just the lock.
Well, no. It's so let's say I just run by myself. Let's walk through that. Okay, I'm thread 0. I set victim equal to 0. Do I have the lock? No, because I go into that while loop. And I say, well, is the victim still 0? Is the victim still 0? Is the victim still 0? You see the problem. I can now, if they happen to execute at the same time, one of them will get the lock. But if I run by myself, then I can't get it. The sequential execution fails, right? So it doesn't work that way. All right. Okay, so the lock 2 satisfies mutual exclusion. If thread I is in the critical section, then victim equals J, and cannot both be 0 and 1. But it's not deadlock free. The sequential execution deadlocks. The concurrent one does not. So now we have Peterson's algorithm. And this is actually the same thing as what we saw in chapter 1 under our third lock attempt. And this is a combination of what we call a CAN and a flag protocol, if you want to remember the terminology. So the idea is I raise my flag signifying that I want the lock, right? And then I set the victim, which is either me pulling the CAN over or resetting the CAN. And now what I'm going to do is I'm going to say, while the other one has their flag up and I am the victim, then I wait. So the way, if a sequential execution by thread 0, I set flag 0 to true. I set the victim to me 0. And now I'm saying while flag J, so while the other flag 1 is up, well, it's not up because this is a sequential execution we're thinking about. It's not up, so therefore I don't wait. I have the lock. Now, once I have the lock, say thread 1 could come in, and thread 1 can set its flag to true. It sets the victim to itself, and now it's going to look at that loop, and it's going to say, well, flag 0 is true, and I'm the victim, so I better just wait, right? Now, if 2 locks come in at the same time, they both set their flags to true. Then whoever sets the victim last, right? Whoever sets the victim last is the one that's going to spin, but only one will get in. So this is going to work, and this is called Peterson's lock. Now, there is a subtlety here. When you actually implement this on a real Java program, it might not work, or it might work just most of the time. And the reason is the compiler looks at this code, and the compiler, part of the reason it fails is the compiler can look at this code, and it doesn't have to respect the order of these things because as far as the compiler can tell, it doesn't matter what order you do things in. But worse, each thread sometimes has its own view of the memory. And they might not be up to date with each other. They might not always go back to main memory to look. They might look at their local cache. And so you actually have to, for these arrays to work properly, you have to use in Java what are called atomic integers. If it's a single integer, you can throw a keyword volatile on it to make sure that this kind of thing doesn't happen. But the flag array might not work correctly unless you're using an atomic integer. And what's insidious about it is it's like everything else. Until you try to have two threads, each try to get the lock 10,000 times in rapid succession, until you do that, it might not fail, right? But as soon as you scale it up to a certain point and you have enough contention, the problem might show up. So you might think that you might write a code and have it run perfectly for years and suddenly fail because you just happen to use it on a bigger problem. So it's a thing to watch out for. Any questions there? All right. So now that you're interested, defer to the other and then wait. Now, the other thing I do whenever I write a program like this and I have something waiting is inside this curly bracket I call thread.yield. And why do I do that? Because the way multiprocessors work, right? Usually, you've got like, say your laptop has 4 cores. Maybe it has more, maybe it's 6, I don't know. But let's say it has 4, right? You're typically doing more than 4 things at a time with your laptop. You've got like, Microsoft Word and your email clients and your browser and all these things are open. At the same time, you're doing these things. And it looks like you're actually running hundreds of threads, even though you've only got 4 cores, and that can't be true. And that's because what your processor is doing is it's doing what's called a context switch, right? It's got the state of all these different threads. And it works on one of them for a while, and then maybe 100 milliseconds later, it swaps in a different one. It's only ever working on, say, 4 of them at one time, but it keeps switching them around so that you can't tell because your brain is much slower. If I say while and I start to wait, right, and I'm in that, let's say it's 100 milliseconds, I'm in that 100 millisecond time slot, I'm just sitting there checking that condition over and over again with no other thread running. It's just me continuously running. It's just a waste, right? The cycles are just getting wasted. It's not going to change until maybe I give up my share, the processor. And that's what thread yield is supposed to do, right? It's supposed to give up your turn. You're saying, I'm giving up the rest of my turn for somebody else to do something. And maybe that somebody else will change the flag or victim such that I can continue. All right. So I always like to put a thread.yield in there. The slides never do that. All right. All right. All right. So so we're deadlock free, right? So a thread is only blocked only at the while loop and only if the other's flag is true and only if it is the victim. And if it's solo, the other's flag is false and it works fine. Both one or the other, but not one of them is the victim, but not both of them. So it's deadlock free. And it's starvation free because if thread I is blocked, only if J repeatedly re-enters. But if J wants to repeatedly re-enter, it has to keep setting itself to the victim. And so that's not gonna happen. So this is going to be starvation free also. If you start to get the lock, you will get it. Make sense? Yes. Yeah, so what happens is in order to reacquire the lock, right? Suppose I lock it, thread 0 locks it, thread 0 tries to lock it. Thread 1 comes in, sets the flag, okay, let's do this carefully. So thread 0 comes in, sets flag 0 equal to true, sets victim equal to 0. Flag 1 comes in, sets its flag true and victim equal to 1. Now the while loop hits and thread 0 gets through, right? Because it's no longer the victim. And thread 1 is blocked. But as soon as now thread 0 is going to unlock, it's going to set its flag to false. Okay, and let's say that at the same time, thread 1 goes on vacation. It just stops doing anything for a while. Now thread 0 comes back to reacquire the lock. What does it do? It sets its flag to true and it sets the victim to 0. So now the next thread that's going to do anything is going to be thread 1 because it's the only one that's not the victim. Right? And this step where I set the victim means that the locks are going to trade. I can't just keep acquiring the lock while the other one is waiting because of the victim. Make sense? All right. Very good. All right. I actually am going to stop here and give you your quiz that I promised you I was going to give you. And I hope it's an easy quiz and it will take you 5 minutes, but I've given you the rest of class to do it anyway. And I have my standard way I like to do quizzes. I like to do everything multiple choice. That way it's easier to grade people fairly, which something I like a lot. At this small a class, it doesn't matter as much for speed, but all right. So first, you get my wonderful bubble sheets. And just pass it back. All right, you're back to the right number on this side. And side. Great, thank you. And let me stop share. Exit.